The amount of movement that we are talking about is at the angstrom level, and the amount of signals that they generate could be in picoamps.
From EE Tech Media and All About Circuits, this is Moore's Lobby. I'm your host, Daniel Bogdanoff. This episode might get a little shaky, but in the literal sense, because today in the lobby, we're talking MEMS, microelectromechanical systems. These are tiny little geometries built on semiconductor chips that can resonate or sense or transduce, and they take some creative engineering to develop. To dig into this tech, we're joined by Fari Assaderaghi, Executive Vice President of Technology and Engineering at SiTime. Fari, thanks for being here today. I'm really excited for this one.
Likewise, really happy for the occasion.
I'm curious, how did you first get into tech and engineering?
Well, maybe a little bit of a background. I grew up in Iran, and I was like many kids, very curious and sort of trying to learn about things. And I was fairly good in math and physics. So that was generally the path that would take you toward sciences. But after I finished my high school, unfortunately, because of the regime change that happened in Iran, and I happened not to be really of the type that they like to allow to universities. I was not allowed to go to university there. So I ended up coming to the US, and in my undergraduate studies, basically I was trying to decide between maybe going toward physics or going toward engineering, but eventually decided to go toward electrical engineering area.
How did you decide electrical over something else?
I think it was because I took a few courses that really piqued my interest in the topic. And also, again, like many other kids, playing with many gadgets, trying to figure out how they actually worked, really piqued my interest at the time.
How did you go from Iran to San Diego?
Actually, my older brother had happened to come to the US earlier, and I was in touch with him, of course, and I was complaining that, hey, look, my path really in Iran is blocked, and I want to continue the education. So he was able to actually get me admission into university, and I left the country, was able to actually go to Turkey because the US embassy actually in Iran was closed. And talking to the US counsel at the time and describing to him that how badly I wanted to continue my education, he took interest in me. And this was actually during the time that relationship between Iran and US was terrible. And he said, son, come back in 3 days and you have your student visa to go to the US. So as simple as that. It was very, very, unusual, and one of those, luck of the draw. That it was a very easy actually process for me to get a visa and come to the US.
What an incredible moment, life-changing moment to have someone vouch for you. That's incredible.
Yeah, absolutely, because as you having kids in the US that are working toward their university education, you build your entire future ahead of you, and you're thinking of what you will be doing. And when that basically is blocked, you think your world is coming to an end. And this was essentially a long shot for me, given that so few people were able to actually get the visa. But I don't know, he found my story. I was a very, very, smarty pants kid back in Iran. And I had, in different exams and so on, had scored so well. So and my English actually was not too bad. So he said, well, this kid really is into science and he wants to continue. So he made it very easy for me.
That's fantastic.
Yeah.
Well, I love when there are people like that we can look back on that have single-handedly changed the course of our lives.
That's exactly right.
So it sounds like maybe grad school was definitely in the cards for you. Is that something you knew you wanted to do, or was that a bit of a surprise?
I was, as you said, there was so much pent-up energy in me now that I had the opportunity to continue. So right after finishing undergraduate, actually I did a summer internship at Bell Labs and had applied to university to to come to Northern California, to Berkeley, to go to university. Actually, just maybe as an anecdote, at the time, head of Bell Labs was Arno Penzias, who won the Nobel Prize in actually shared the Nobel Prize in actually confirming the Big Bang Theory. So it was a very, very interesting introduction at the time for a bunch of summer kids at Homedale and in Murray.
That's crazy. Yeah.
Yeah.
Was that intimidating or exciting or a little bit of both?
He actually was incredibly friendly. Incredibly friendly. So at the beginning, we have that element of awe, but he was so, unassuming and sort of humble that after a few minutes, that sense goes away.
What did you end up studying at Berkeley?
Right. So I actually, when I went to Berkeley, I started with communication theory. And that very first year that I was working with a professor named Praveen Baraya, as a fantastic professor in the field. And actually, just as an anecdote, we were working on a program called PATH, which was Platoon of Automated Transportation Highway or something like that. It was actually sponsored by Caltrans. And we were trying to demonstrate that you can drive a platoon of cars with only the first one having the driver and the driver basically, and the others would follow in a short distance in between and rely on communication and automated braking and speeding to keep the distances. So it was really a precursor to this whole concept of autonomous driving. And actually it worked. We put tons of electronics, custom communication, laptops and PCs, not actually laptops, PCs, into each one of these cars. And we demonstrated this thing, I think on Highway 15 in San Diego. 4 cars going down the freeway with, I think, a meter distance in between them going about 80 miles an hour.
Wow.
So, but this was, I think, Dan, this is similar to many other technologies that the ideas always have existed for a very, very long time. But it's really how mature the technology is and how it has reached its sort of capability to make something from a novelty to actually a usable technology. So I started with, so I stayed in that field, the communication area, for a year with Professor Baraya. But then I was taking classes in quantum mechanics out of the physics department and semiconductor physics, solid state physics. And I absolutely fell in love with the subjects. So I went to Praveen and to a professor named Chen-Ming Hu. And I said that if it's okay with them, that I want to switch field and go toward the physics of semiconductors. And both of them agreed. And Chen-Ming, of course, is a luminary in the field. He's well known as someone who has advanced the field of semiconductors in many areas, from compact models. For example, if people use SPICE for circuit simulation, the underlying engine for that, for the simulation, is something called BSIM, which is actually Berkeley's innovation and was developed by Chen-Ming and his group. And he's also known as a father of FinFETs, that he made large contribution to that area. So it was really a hoot for me to join his team and do my PhD work with him.
What a special time and a special group of people to get to learn under.
No, exactly.
So after Berkeley, you went to IBM. What was it like moving from the world of academia to the world of enterprise business?
Yes, so I was actually, when I was at Berkeley, I was working on a technology called, my PhD work was actually on SOI, silicon on insulator. And it happened that IBM research was also looking at the field, basically as a technology that allows VLSI to be built with lower power. One of the key benefits that SOI provides is that we have so-called lower junction capacitance in transistors. The capacitance is smaller, therefore you burn lower power when you switch the devices. So they were working on the area, and so I joined to continue the work actually in the field. But IBM research was really like a wonderland. So many great people there. It was like, I don't know, probably thousands of PhDs working at IBM Research. And some of them I'm sure you have heard of. Bob Denard, I don't know if the name rings a bell, but he's the guy who actually invented single transistor DRAM cell. And is one of the guys who is known for sort of writing the transistor scaling theory, that you go essentially a supporting technical analysis of the Moore's law of how you actually scale the transistors through constant field scaling. Also, at the same time, this was actually just a coincidence that this was the same time that Lisa Su, the current CEO of AMD, she was there. She had also finished her PhD and was working at IBM. So I continued working on SOI, and she was actually working on development of the very first copper backend. People probably don't recognize, but IBM did a lot of pioneering work on semiconductors. Like the first introduction of 248 nanometer lithography was done by IBM. SOI was done by IBM. Copper, so basically this dual damascene process, that copper became the backend material for all of ICs, was actually first introduced by IBM. So this was really a heyday of semiconductor research within IBM. But semiconductor was only one portion of the activity, was part of what they called physical sciences. They had great scientists in mathematics and many, many other areas.
Interesting. Yeah, I just always assumed copper was the go-to material, but I suppose it had to become standardized upon at some point.
Yeah, exactly. But just maybe 30 years ago, it was all aluminum backend.
Were there any standout differences or similarities that strike you about working at those two world-class places? You went from Berkeley, which is, doing crazy research, discovering elements, to IBM.
I would say the similarity is that both of places were incredibly rigorous in terms of going after things from first principles. Really go to the bottom of the science that describes something, and from there go and solve the problem. But obviously, IBM had the commercial angle to it. There were many mad scientists that you thought that, hey, would they ever produce anything that IBM can sell? But at least ostensibly, that was the mission of the IBM research, that it was tied to the businesses, and the technology that was being developed was supposed to be looked from the commercial angle. But it was, both of them really, the quality of the scientists was really first class.
So how then do you go from Berkeley to IBM to SiTime?
I should describe something about myself that I always tell people, maybe a little bit tongue-in-cheek, but I think a large portion of its reality is that I really don't have any talent, but except for curiosity and really love of learning. That has been probably the only characteristic that I've had. And I always want to, and if you look at my career, is that I have probably changed more than typical engineers you would see, is that I always want to learn something new. And although IBM was really a fantastic place to learn a systematic approach to problems, processes, and methods to follow, and so on, it was still a large company with that sort of a slow nature to it. So I wanted to try something more of, come back to Bay Area and to California on sort of a startup atmosphere, smaller companies, faster pace of moving, technological disruptions, and so on. So that's why I came back to California. And first I was at Rambus for a few years before coming to SiTime. Maybe just as an overall course of my career, I would say I have spent almost maybe 10 years in semiconductor physics, in device modeling, another 10 years maybe in analog, mixed signal, high-speed communication and high-speed interfaces, and another 10 years in MEMS.
Well, I am chomping at the bit to get into MEMS, but it's time for a quick break. We'll be right back. This is the last episode of Season 6 of Moore's Lobby. We'll be back in September with Season 7. But if you're like me, you're always looking for more engineering podcasts with some technical depth. And I have a good option for you. Thanks to this episode's sponsor, EBV's podcast called Passion for Technology. They have some great episodes over there exploring hot topics like silicon carbide and gallium nitride devices, motor control, EV charging, analog and power chips, and a lot more. So wherever you get your podcasts, search for EBV's Passion for Technology podcast and dive into the world of semiconductors. And now back to our chat with Fari Assaderaghi, Executive Vice President at SiTime. So MEMS devices are fascinating to me. Could you give me a crash course for listeners who maybe aren't familiar? And then I'd love to hear about some of the early days of that development.
Sure. People use many different terminologies for this. Sometimes people call them transducers. Sometimes, as you are saying, they call them MEMS for microelectromechanical systems. But the name actually is fairly self-descriptive, is that you have these tiny structures that are in the micrometer dimension or tens of micrometer dimension, and they have mechanical characteristics to them, but also they eventually transduce these to electrical signals. And they are essentially to a large degree, our means of communicating with the physical world, going from physical world to the digital world. You can, for example, if you consider a MEMS microphone, it transduces basically sound to electrical signals that you have. Or gyroscopes, they are measuring angular motion. Accelerometers, they are measuring linear motion. In case of SiTime, we actually have these tiny structures that you can think of them in a very crude way, like tuning forks, extremely small mechanical structures that they have vibrations or resonances that are maybe in sub-nanometer range or nanometer range, but somehow we are able to pick up that very tiny amount of mechanical vibration, convert it to electrical signal, and beyond it, then you are back to the electronics domain of filtering, amplification, signal processing, and so on that you do afterwards.
Yeah, it feels like a bit of magic to me. Like I've seen magical engineering, but MEMS devices for some reason are just such a it's hard for me to wrap my head around motion at that micro scale or nanoscale.
Exactly. Sometimes they literally move in angstrom level. The amount of movement that we are talking about is at the angstrom level, and the amount of signals that they generate could be in picoamps of current that you are picking up, and you are trying to distinguish that among the noise, amplifying and doing the rest, and so-called closing the loop.
Yeah.
And the very interesting piece on this that people maybe do not immediately recognize is that silicon, people have thought of silicon as a fantastic semiconductor material for electrical properties, but it actually turns out to be a fantastic mechanical material. And that's the whole magic of the MEMS, is that you rely mostly, not always, you have other structures besides silicon that is being used as MEMS, but mostly people use silicon as the material of choice. And it does two things. Of course, it has many nice characteristics in terms of fatigue and so on, but it lends itself to a lot of semiconductor processing capabilities. That is the hidden benefit that actually MEMS really piggyback on, that many of this entire ecosystem that has been developed for standard CMOS processing and so on can be reused, both in terms of the manufacturing infrastructure, but also a lot of it through the EDA tools and so on that you can bring into the field of the MEMS.
It makes sense. Like, we know how to make chips, so why not etch them, chemical mill them in a way that they wiggle a little bit? To put it
Exactly,
roughly.
exactly, exactly. Actually, then just as an anecdote, I was at a VLSI symposium. I'm still on its committee, and they are describing the ribbon fits and nanosheet transistors that are for the 2 nanometer and 1 nanometer technologies. And actually, many of these now have to do crazy stuff that MEMS do in terms of etching and removal of the layers and sacrificial layers and temporary bonding and so on, that the MEMS folks like us had to figure out a long time ago. Now on these very advanced CMOS technologies, they have to revert to those techniques.
So it's almost wrapped back around. It became its own branch of research, and then that's folding back into mainstream manufacturing. That's really interesting.
Exactly.
So let's dig into the history of this a little bit. You joined SiTime in 2008. What was the state of the company and the state of MEMS at that point in time?
The company was quite small. I forgot the exact number, but we definitely were sub 100 at the time. We had demonstrated maybe the first working device, but it was really, in terms of performance, was nowhere near quartz technology. But sort of the premise was this, that like many other legacy products, we thought that there is a much better way than, I don't know, quartz, that you take a piece of rock and you polish it to special dimensions and that becomes your frequency reference. We thought that there is a better way to build the devices, new technology that both allows you to advance the performance and characteristics or bring functionalities that you would never be able to achieve with quartz. So that was the premise. As you could imagine, the disruptive technologies, a lot of times, they come from the low end. Very rarely you see that a technology that kicks out the incumbent comes from the higher performance. We came out from the low end as well. But they have some sort of an inherent advantage. And I think we had multiple inherent advantages. One of them was that our sort of cycle of learning and cycle of improvement is far, far faster and more superior to cars that you had. So if I look back in 2008, we had a device that barely, if you looked at it the right way, met 50 ppm, 50 part per million of stability. Now we build devices that are in the part per billion. So over the course of 15 years, we have improved close to 100,000x.
Wow.
That's like on stability. You look at other timing parameters like phase noise, like jitter, like Allen deviation. All of them, we have not improved by 5x or 10x. They are like in tens of thousands or millions of improvements. So this sort of very fast cycle of learning that doesn't exist in quartz was a huge advantage. The other advantage that we had, the same methodology. Right now, if you design a 100 billion transistor chip, if you use the right simulation method and you verify it, you submit it to the fab, it comes back and it works as expected. If it doesn't work, you think you have a bug. It is considered an unusual characteristic. So on the MEMS side, we applied the same approach, that our design environment, our prediction capability, we kept on improving it such that first time right, that when you get your device first time right, and the level of accuracy that you can actually achieve with it approaches the same thing that you have in the semiconductors. This was, I think, the second one. The third one, I would say, is that we had sort of these incremental improvements, followed by a quantum leap improvement. And then again, this evolutionary improvement followed by another quantum leap. And I think that has led us over this past 15-year journey to eventually get to the performance level that we are at right now.
As much as I want to dig into these quantum leaps, I imagine there's a lot of IP there. So instead, maybe a better question is, Are these things hard to build? What's it like when you go to fabs and ask them for weird architectures and processes?
Imagine it is in IC industry that if you develop a 0.18 micron CMOS process, you can build many products on that. You can build analog parts, digital parts, RF parts on that. MEMS tends to not lend itself to that. So a process that is optimized to build a timing resonator is likely different than a process that is optimized to develop an accelerometer. So by definition, MEMS companies need to also work on development of the process that is used for making the devices. There is no such a thing to a large degree of a platform process technology for MEMS that you can just submit your design and you get your MEMS back from it. You actually literally need to think between the two, between your design and the process in terms of the overall end result that you're trying to achieve. And SiTime is no different than other companies in that. So all of the products that we have developed, we actually thought of the processes needed to build them, worked on the process development of that, but we transferred them to manufacturing partners that eventually have that process established and use it for production.
Did those manufacturing partners look at you like you were crazy when you came to them the first time? I imagine that'd be an interesting conversation.
Well, as you know, the two founders, Aaron Partridge and Marcus Lutz, both of them worked with Bosch. So fortunately, they did have the experience in that area, and therefore there was some level of familiarity and affinity toward this. So they had one leg up from that perspective.
They knew what they were getting into.
Exactly.
How did the markets react to MEMS, and who were some early adopters that really got it?
Initially, there were still some advantages to our devices. Is that our devices have PLLs in our devices and fractional NPLLs in our devices. We could make our devices programmable. And therefore, defining or specifying a slightly different frequency that the customer wanted was very straightforward for us. Preparing that and delivering to them on a very short time basis was very straightforward for us. So the ones that were not pushing the envelope in terms of performance, they were able to use our devices, let's say multifunction printers and digital still cameras and so on, that were really not pushing the jitter or phase noise at a time, and the stability of 50 ppm was acceptable to them. They could use our devices right away. So we got some early successes with those customers.
Okay. So basically putting a phase lock loop in there gives you some capability to adjust frequencies. Were you also doing like ovens and that sort of thing to adjust temperatures, or was that more of something you had to compensate for?
No, we had built-in temperature sensors. So as I described earlier, because the MEMS frequency was shift with temperature, so how do you actually correct for that? So you build a temperature sensor very close to the MEMS. You do basically a temperature to digital converter, so a TDC, and then you feed the MEMS to oscillator output to a phase lock loop, and you adjust essentially the divide ratio of the phase lock loop based on a temperature information, and you stabilize the output. So that's how we initially achieved the desired stability that we could get.
So I want to keep exploring MEMS in your time at SiTime, but I, no pun intended, but I also saw that you spent some time at Invensense and then NXP. Can you tell me about what pulled you away from SiTime and what you were doing at those other companies?
So Invensense, it was just trying to round out my knowledge of MEMS and expanding my overall expertise in the area. They were not working on timing. They were working on different type of MEMS. They were working on inertial sensors. These are gyroscopes and accelerometers. And actually there I worked on microphones, MEMS microphones, and another technology called PMOTs. PMOT stands for piezoelectric micromachine ultrasonic transducer. So PMOS are yet another MEMS transducers. They actually launch ultrasonic waves. You can have as high of a frequency as 100 kilohertz, not in the hearing range, or even a megahertz. And the wavelength of sound in those cases, like in the 10 megahertz, could be in few micrometers. So you could use them actually for fingerprint detection.
Huh.
People remember, like, for example, they use old fingerprint sensors were based on capacitive sensing. And capacitive sensing, you have a trade-off of the amount of insulation that you put between the sensor and actually the finger. With ultrasonic transducers, you could go through any material. You could go through glass, you could go through metal, you could go through many other ones. So we essentially created an array of these little PMOS, like little drum heads, that they would launch ultrasonic waves, and you could apply techniques used on phase array antennas, that you could literally do phase shifting and beam forming and literally move the beam to scan the finger.
That is super cool.
And this actually worked. The technology actually worked, but it was quite expensive. So maybe the only lesson I learned from there is that developing the technology for the sake of the technology and creating a very cool gadget, but missing what the end customer requirements on cost are, is not a very sound business strategy.
Yeah.
So I worked on PMOS, I worked on MEMS microphones. Also, I worked on even gas and chemical sensors. You can do on MEMS. You can build gas sensors by, again, having isolated structures that by heating them, metal oxides, you can make them sensitive to different type of gases. On NXP, I think it was just, for me, was that a very large company with tens of thousands of engineers, and they wanted to me be the CTO of the largest business unit that they had. So I thought that I should get a sense for a much larger organization running a much larger engineering scale would give me an interesting view. So I did that, but actually, honestly, I realized, maybe after a few years, finally I realized that my calling is with smaller companies, closer to the startup environment. And one thing really that brought me back to SiTime is that, honestly, the culture of SiTime is unique. An incredibly interesting company, and really this has been instituted by Rajesh right from the beginning, is that openness of the environment, the ability of people to take risk, and actually ability to fail. Many companies say that. Many companies say that. In reality is very different. Yeah. Reality is very different. And SiTime to this day has really stayed true to that characteristics, that you get encouraged, you get actually rewarded by taking initiative and actually failing. I have not seen a single person in this company ever getting fired for failing at a technology or an initiative. Actually, most have been promoted through the process. So from that perspective, is a very interesting company. And I would say there is one element, maybe would be a good message to other engineers, is that as engineers, a lot of times we bound ourselves very quickly to what is possible when we are being asked if to do something, and is that we immediately jump in, is that, hey, what are the things that are possible and which parts are not possible? What Rajesh says at SiTime, and this I found it as really, really incredibly valuable, is that we should start with what you want to achieve. What is your goal? what is the ultimate desire, and invariably in the process we have figured out a way. That's is like, you may say this is a slight difference, but it makes enormous difference in the attitude that people bring into a problem and how they define the box that they are playing in. You don't get really very quickly pigeonholed that these are the tools that I have in my toolbox to work on. And that is, I think, a key characteristic of SiTime that I have found it always very, very interesting.
It's not super common to come back to a company that you have moved, to another role from. So to come back knowing what you're getting into, it must be a good thing.
That's right. That's right. Yeah, and most of the people here are from the time that I left, and Rajesh and I have been friends for all these years in this, and both the attraction of the company, and I think is at a place of that it really is scaling, that we have hit the inflection point and huge growth that we have in front of us is scaling. And I think that's probably an element that I can add to the mix. Is now that I have run organizations much larger, I feel very comfortable.
Yeah. Is there anything that surprised you when you came back about the state of the technology or discoveries that have been made, anything like that?
Exactly. Is that actually the company has been quite good at keeping some of them secret. Is that, I mean, they are all friends, and every now and then I would get together with them over lunch or dinner or beer, and I would tease them, wow, that this performance is amazing, and it must be, you guys must have done it this way, and they would only laugh, and they would not tell you. So now that I have come back, I know the secret sauce.
So you had to come back so you could find out what they were doing. So clearly we're beyond the performance of quartz. Can you kind of describe the state of MEMS as it is today in 2023?
I would say that vast majority of the parameters, we are superior or far superior to quartz. There are some places that you would say still they could have merit over us. But I think from that perspective, largely the game is done. The piece that I would want to sort of maybe discuss related to this is that where we go with MEMS and where the direction of the MEMS is. I think at some point we were sort of maybe lagging the market. At some point we met the market and we were at the market. Now I believe we are leading the market. And one thing I would want to mention is that it's not only getting to the quartz performance, but capabilities and categories you can create that are never possible with quartz. It's like when you think about like Uber and taxi, you say, well, I mean, are they comparable? In some metrics they are, but in some areas, Uber provides a functionality you could never get out of a standard taxi. Same thing with MEMS and our technology. With this combination of the MEMS structure, the CMOS electronics, and what we do with the packaging, we create sort of categories of products that were never possible in the past. And you probably have seen that we have built this, what we call MEMS Super TCXO. It's a TCXO device. So it doesn't have ovenization. It burns few milliamps of power, but it is at the same performance that with quartz you have to ovenize. So you can imagine in terms of robustness, environment that you can operate it at, power that it can burn, the form factor that it has, it enables use cases you could never achieve with quartz from that perspective. But back to where the MEMS is going is that now it's sort of believing that we are leading the market. The important piece is that actually timing is very critical piece of the entire electronic systems. From the sensing piece that I described, to the communication, to computation, to storage, timing is like an unsung hero that is behind the scenes, but its performance actually limits or enables certain performance characteristics that you see at the end systems. So we really want to look at the trajectory of many of these fields, let's say optical communication and so on. They are marching towards certain bit rates and certain communication rates and so on. There ought to be a commensurate improvement in timing. So we want to make sure that what we generate, what we build, essentially is becoming enabler of these many different technologies from enterprise to autonomous driving to high performance computing and so on. They would need certain timing needs, and we want to make sure that we are at the leading edge of developing that. That's on the application side. I have not seen, looking at the company over the past 15, 16 years, I have not seen a slowdown in our performance improvements. So back to Moore's law and Moore's law, I think we are on our own Moore's law of timing improvements.
Ooh, yeah, there's a soundbite right there. And there's got to be a point where you've addressed the conventional use cases, but you don't really know what happens when you get to higher performance and maybe what we'll need in 20 years.
Yeah, I can tell you that exactly as what you're saying is that back to, transistors or computers that people said, who needs this level of performance? And you always have found cases. You can imagine, for example, in the area of navigation and overall location determination, the timing plays a very critical role in that area as well. And getting better and higher precision timing will improve that dramatically.
That's how ships used to navigate, is with clocks and wind speed, basically.
Exactly.
Were there any applications that were just a surprise to you? You didn't really expect people to use MEMS that way?
Not really surprised me, but I would say that the area that is getting a lot of traction for us is in the area of aerospace, military and defense, and so on. And that's because the ruggedness, the robustness of MEMS devices against shock and vibration and very large environmental temperature changes is a huge differentiator. That you can imagine these devices that we have, the MEMS resonators, mass probably is in the nanograms, and by definition makes it incredibly robust against these shock and vibration conditions. So that area is a area that is finding a lot more use of our devices for them. And similarly, we are seeing a huge adoption for autonomous driving and for EVs. Those are the new areas that are not surprising, but we are seeing a huge amount of adoption taking place.
As we wrap up in time, we like to do a lightning round, some quick questions that may or may not be related to the conversation we've had already.
Sure.
First question, are there any cases in pop culture that you feel really get technology right or really get technology wrong?
Maybe it's my personality that I always find these sort of science fiction movies really annoying.
Yeah, same.
that I find that they so oversimplify or make things up that it is really, I just want to yell at TV that no, it doesn't work that way. But actually, the thing is, even when I was a kid watching Star Trek in Iran, seeing some of those technologies actually coming pretty close to reality is amazing, actually.
Yeah, it's hard to suspend disbelief as an engineer because we're trained to try to, dig into it.
Exactly. You said it better than I did.
So you did at NXP have some time in a security role. Was there anything that surprised you doing that? And how has that changed your perspective on your personal security?
What I learned was that you make this very complex method of multi-layers of defense to protect a device, secure enclaves and many sentient circuits that are actually watching if something has gone wrong or no. But actually, most of the flaws and weaknesses are trivial. They are not because you have had a cryptographic algorithm that has a weakness in it, but actually open ports and really stupid implementation errors that have left the whole barn door open. That 90% to 99% fall into the trivial category rather than the ones that a lot of PhD researchers are working on. Now, you know that they are developing quantum resistant, basically cryptographic algorithms. That they are thinking that the quantum computers and Shor algorithm and so on are going to break conventional, triple DES or AES-based cryptography. And maybe true, maybe in 10 years or 15 years they can do that. But vast majority of weaknesses are of the bland version.
It's like the gate that's 3 feet tall but has a really nice lock, and all you have to do to open it is just reach over the fence and turn the handle from the inside. To close out, you have worked with some very, very notable people, Nobel Prize winners, like you mentioned earlier. What's the best advice you've received from a mentor or someone you've worked with? And what advice might you have for someone who's starting out their career in tech?
So maybe the first one I would say is from maybe Chen Ming and similar experience at IBM, is that always go back to first principles. If you don't understand something, don't paper over it. Keep on digging, keep on convincing yourself till you get actually to absolute fundamental that you know it is correct. Really go back to the first principles that you have learned. For engineers, any time that you rationalize, it's going to come and get you. There is no shortcut, and if the fundamental doesn't support it, eventually it's going to come and get you. That would be one. The other one actually is what I mentioned from Rajesh, which is sort of don't box yourself in too quickly. That a lot of times we have this tendency of defining what the possibilities are. If you start with what you want to achieve, what the ultimate goal is in terms of performance or characteristics, put that as the goal, you would be surprised. And I have seen these things so many times, you would be surprised that eventually what you thought was not possible, actually it is possible.
I love that. What a great way to wrap up this podcast. Thank you for being here today.
Thank you so much.
That was Fari Assaderaghi, Executive Vice President of Technology and Engineering at SiTime. So that's it for today's episode, which was the last episode of Season 6. But don't worry, we'll be back in September to kick off Season 7. So make sure you are subscribed to this podcast and follow both Moore's Lobby and All About Circuits on your favorite social media platform. And while you're there, sharing this podcast with other folks is always greatly appreciated by me and the incredible Moore's Lobby team. Shout out to Tara and Dale. This podcast would not happen without them. It also wouldn't happen without you, so thank you for joining me today in the lobby. I'm your host, Daniel Bogdanoff, and did you hear about that traffic cop that only directs big rigs? Yeah, I looked them up on LinkedIn and their job title just said semiconductor. Have a great summer. I'll be right back here with you in September for Season 7.